Our speaker this morning, Joe Talmadge, um, has been actively engaged in some of our discussions before this, and he's quite interested in fusion. And I'm delighted that to have a review by someone with his expertise, because um, we we keep hearing about cold fusion and then we hear about delays in Cadarache, France, because of some fires, and then so we hear a number of conflicts over when fusion might be available, and it's really good that we have Joe here today to fill us in on the realities of fusion. So uh, I'll let Joe. I haven't reviewed in detail your curriculum vitae, but if you'd like to make other comments about your background and how you got interested in fusion at the beginning, that would be welcome information for us all.
Actually, I have some slides, just a few after this, and I'll just talk about myself then.
Sure.
So it's coming up, actually. I'll show you some pictures of the machine we built and so on.
Good. Well, you have the floor.
All right,
So
thank you.
that's just great. Thank you for agreeing to do this, Joe.
Sure, no problem. Um, yeah, the only thing is sometimes um, my voice is going a little bit, so I'll be drinking a lot during this talk. But I guess what I wanted to start out with, so you can see my screen properly,
Yes.
right?
Yes,
Great.
so, clear. Yep.
So I don't know how many people actually actively keep track of fusion, but at least some of the headlines, sometimes they're forced upon you anyway. So you might have seen, you probably saw the one in the upper left corner, because it was on all the front pages of the news, which is that scientists achieve nuclear fusion breakthrough with a blast of 192 lasers. And that made the news worldwide, actually. This was in 2022. And some other headlines. I just copied off these headlines, which is that 69 megajoules jet sets fusion energy world record. Artificial sun sets record for time at 100 million degrees. This is one of my favorite headlines. Microsoft agrees to buy electricity generated from Sam Altman-backed fusion company Helion in 2028. Now, this was made, the statement was made actually in 2023. So in that 5 years, they expect to have a full fusion facility that they're going to sell to Microsoft. And finally, on the bottom, the fusion industry outlines ambitious plans to deliver electricity to the grid by 2035. So with all these great headlines, the question is, why isn't fusion online now? What's taking it so long? What are the problems with fusion? When or if fusion will ever come online? And so I wanted to give a talk about what the status of fusion is. And I'll say first off, I'm a fierce advocate for fusion, but I'm also a realist. And so hopefully I'm going to give you a sense of what some of the great aspects of fusion are, but also something that's not always talked about in a lot of fusion talks is what are the real problems that fusion is facing. So hopefully you'll get some of that feel from my talk. And my personal interest, especially in fusion right now, is a climate crisis. And my hope was that fusion would eventually be able to meet that challenge. And so, for example, there have been a number of agreements. For example, in 2009, the Copenhagen report, which said that the increase in global temperature should be below 2 degrees Celsius. Paris Agreement lowered that even more, said really we need to limit the temperature increase to 1.5 C above pre-industrial levels. So the way I frame my talk is, will fusion help limit the mean surface temperature increase to below 2 C? So why didn't I say 1.5C, right? Because that's what the Paris Agreement says. Anybody have an opinion about that? And the answer is that we'll probably hit 1.5C next year. Actually, this year, 2024. There's no chance that fusion is going to have anything to do with 1.5C. Even if we hit 1.5C in 2024, it doesn't mean actually that we're there because there's a lot of natural variation. So the question is, over a period, what's the long-term average? So when do we really hit 1.5C or not? But the probability is that most of the databases now will show in 2024 that we've already hit 1.5C. And I think actually Berkeley Earth, which is the database that I usually follow, they had 2023 already at 1.56. They're usually a little higher than the others.
I have a quick question, Joe. When you talk about pre-industrial levels,
Yeah.
you define that a little more accurately?
Yeah, that's a great question, actually, because it's not really that pre-industrial. I'm actually defining it the way the IPCC defines it, which is the average temperature from 1850 to 1900. That's not pre-industrial, actually. So if it was really pre-industrial, you would have add another, I don't know, at least 0.3C or so to it. So if you took the average of temperatures from 1850 to 1900s and you look to now, we're about 1.5C.
Okay, thank you.
Yeah,
So,
that is a little confusing sometimes.
yeah,
So on the left, you could see a graph of what the CO2 emission is from fossil fuels. Let's see, you can see my mouse. Here's a fossil fuels, and this is from land use change. And the total CO2 emission, which is up to 40 big gigatons, is this blue line here. And the thing that always kind of amazed me, if you look at this graph, is that the emission from fossil fuels didn't exceed the emission from land use till about 1950, which was quite. I discovered this like by myself like a few years ago when I was looking through some of the data, and I realized it's quite astonishing that it took that long for it to exceed the CO2 just from land use alone. And I typically just when I look at CO2 emission, I include the land use changes, and this is something that. Go
could I
ahead.
ask another question?
Of course.
Really impressed with land use changes dropping off in around 1960 or so. What sort of practices were used back then that made such a dramatic improvement?
I think there was a lot of clear cutting of forests, for example,
Okay.
and some of that's getting better, but that's probably most of it right there.
Okay.
Yeah, that's a good point. So I took it upon myself to sort of get an idea. I mean, you could see it. You can even see it in here. You don't have to do very, very much fancy mathematics to see that actually you could see this real nice exponential rise in fossil fuel emissions. And quite frankly, if we were going to continue that exponential rise, the world would be a much more dangerous place. Well, let's see, after last week, I'm not sure exactly how much more dangerous it's going to be, but let's put it this way.
Yeah.
We're certainly the prospect for keeping the temperature in some reasonable limit, like hopefully like below 2C or 3C or whatever. Here we were, if you just extrapolate from here, we're going to go up to 5C or something. And the good news is that all those scenarios, like the worst scenarios that the IPCC had, basically aren't going to happen. And mostly because coal use is really on the decline. Actually, this is something I did, like, I think it was in 2020, so I don't have all the data, but I didn't want to feel like I wanted to redo this, which is I use this technique called change point analysis, which basically it looks at the trends in the CO2 emission. It tells you when there are breaks. And so you can see, so I've sort of cut them up into different segments as to when there are change in the breaks and so on. And you can see that the doubling time for CO2 through a lot of these periods was pretty much on the order of 30 years, that in 30 years' time, CO2 emission would double. All right. So there's two interesting things. One is, so here you can see that, and I only did this out to 2019. If I just put on the rest of the few more data points beyond this, it still doesn't change the data very much, but you can see that the doubling time has increased to 100 years. So that's great. I mean, that's good news from 30 years to 100 years. So here's a question for people. Look at this region right here from 1992 to 2002. So CO2 emissions slowed down in that period. So the doubling time was like 50 years. It almost doubled from previous decades and so on. So what happened in the 1990s to cause the CO2 emission to sort of fall off a little bit?
This is global, correct?
Yeah, this is a global ride, of course.
Yeah.
Anybody? Dissolution of the Soviet Union.
Okay. Oh, thank you.
Shut down a lot of the coal plants and so on in Eastern Europe. So you could see history right here in the data as to what was going on. I actually had made a plot too that if you look sort of the derivative here of the sort of CO2 emissions, I didn't bring it for this talk, but you could see every little economic catastrophe that the world has ever had, since 1850. The Deep Depression, COVID and so on, all comes out from little spikes downward in the CO2 emission. So you can, anyway, anyways, it was sort of interesting to see this little bit of history right here in the 1990s.
That's fascinating. We started to buy their uh, uh, rocket warheads about that time to replace
Exactly.
the mining over here, but that's just a little sign. What you're pointing out is the more important thing of the whole Soviet Union collapsing. Fascinating. Thank you.
Right. That's actually a huge point too, Richard, just that it was a nice period where we were taking a lot of the Soviet warhead fuel and basically reprocessing it. Some of it, I think, may have gone to reactors. I'm not sure. What do you think, Richard?
Yeah, I don't know about the reactors. It was the warheads, but they just had to dilute it because
Yeah,
warheads were up around 95% enriched. So they
yeah,
just diluted it down to 20% or whatever they wanted.
yeah. Okay. So the good news is the growth in the CO2 slowed over the last decade, and I don't want to minimize that. That's a huge
Yeah.
achievement, you know, which which really prevents future generations from experiencing some of the worst of climate change. But the bad news, of course, is that it's not nearly enough. And we need to not only have this thing slow down, stop, and turn around again. We need to make it go down. So that's where fusion comes in. So that's my interest. So I got one more slide. Um, so basically, I wanted to, rather than just say 2C, I wanted to put a date on it. And so here I graphed some of the IPCC's, what they call the SSP, Shared Socioeconomic Pathway. I can never remember that. They have these different scenarios for how CO2 emission might evolve from here to the end of the century. So the good news, what I'm trying to say was that, these regions out here of, 7 and 8.5, let me tell you, by the way, what these numbers mean. 8.5, it means what the forcing is from CO2 out at the year 2100. So forcing is just a term used that's in watts per meter squared. So you could see as there's more CO2 pumped into the atmosphere. So here's up to 120 gigatons per year. So the forcing here would be 8.5 watts per meter squared. So what I wanted to point out, so the black curve here is the actual real data up until last year. And you can see actually it fits exactly on this curve here, which is SSP2 4.5. So 4.5 means 4.5 watts per meter squared out at 2100. So the fact that that it fits so nicely to this emission scenario, that's what I'm going to use as to when we're going to get to 2C. And so here are the temperatures that correspond to these emission scenarios. So this one up here corresponds to the 8.5 case. And you can see this one would have doomed the planet, basically, would have gone up to like 5C. This one a little less worse off, up to 4. And then the one we're heading on is basically looks like at around 2.7 by the end of the century. And some of these here, actually, you're pulling CO2 out of the atmosphere already, to scenarios to keep it under 1.5 even. But I think right now we're on this trajectory here. Whether we're going to stay on this trajectory, of course, is an open issue, but it sort of gives us a baseline for what we want to shoot for if we're going to keep the global temperature below 2C. So here you can see in this scenario, for this IPCC scenario, we basically get to 2C around 2050. And this scenario says we will get to 1.5C at 2031. And of course, we're going to get there this year. So this is a little too optimistic in some ways. And the important point is actually, I pay attention a lot to what Gavin Schmidt, he's the Goddard Institute of Space Studies, head of division of NASA. And, basically he's very blunt in saying, we all know that we had a large El Nino event in 2023, but he's pretty upfront by saying, it's that the temperature in 2023 jumped so much that just the El Nino itself doesn't quite explain it. And he really doesn't have a great an answer right off with the data to back it up, to say what actually caused this huge warming for 2023. And we're going to see it again continue in 2024. So that's the way I'm going to frame my talk then. Where would fusion, is fusion going to help us keep the warming limited to 2C by 2050? And to do that, that implies that we need some sort of first of a kind commercial fusion reactor by 2035 to help prevent 2C warming. And my talk is going to be about, is that even feasible?
I just a quick
Go
question,
ahead.
Joseph.
Go ahead.
What those units, what do they really mean? It's watts per surface area?
No, it's watts per meter squared.
Yeah, but what is the area for their surface?
Yeah, right. So if you wanted to see what the total energy, so there's an energy imbalance, right, between the heat that comes in from the sun and the fact that there's a radiation transfer in the atmosphere. So that CO2 comes up from the ground, gets absorbed by CO2, and then re-emitted, propagates up, absorbed, re-emitted all the way to the top, right? This is radiation transfer. So basically, what happens is the CO2 basically as more and more CO2 piles up, what you see is that if you were looking down with a satellite, say on the Earth, what you would see from the 15, I think it's 15 angstrom CO2 line, that it would be getting cold, it would be dropping out, it would be getting colder and colder, this CO2 line, meaning less and less emission would be coming out from the Earth because of the CO2 that's sitting there, absorbing it and re-rating it. But as you go up, the atmosphere cools as you go up. And so the emission so you get very little emission at the top of the atmosphere. And that's the reason why there's an energy imbalance. If that makes
Okay.
sense.
I still don't quite get it, but
so let's
I'll
put
think
it this
about it.
way. So the forcings are typically in units of meter, is watts per meter squared. Basically, you look at the sun input. Basically, if you wanted to get what the total energy is, you just divide it by this. You just multiply it by the total surface area of the planet. That would
Got
tell
it.
you how much energy is getting through.
But okay.
And we know actually about that there's an energy imbalance because you can tell specifically how much the ocean is warming up. So most of the heat from this energy imbalance is actually in the ocean.
Right.
So for example, if you plot the data of the ocean temperature as a function of time, and you took the slope of that line, basically that, and then you divide that by the surface area of the planet, that tells you that there's an energy imbalance of 1 watt per meter squared. That's what the energy, and so that means that the Earth has to warm to compensate for that energy imbalance. It has to radiate more
Okay.
in the regions outside of where CO2 is absorbed, especially in this atmospheric window where nothing gets absorbed. Okay, so it's just a convenient unit for force. It's what's called forcing.
Of course. Yeah.
Okay.
Okay.
I'm
Got
not
it.
sure
Thank
if I
you.
did that well, but hopefully.
Okay. That's good. Good
Mhm.
enough.
Yeah, and I was going to tell people, if you have questions or something, please just shout them out because sometimes I don't always pay attention to people raise their hands. So just shout out any other questions. So I was just going to tell you about myself a little bit. So I'm a plasma physicist. I got my doctorate in the physics department here at the University of Wisconsin. I spent my entire career working on one type of fusion experiment, which is called the stellarator. And I think it's beautiful, but this beautiful machine here, we built this machine about 25 years ago. It's still operating. It's called the helically symmetric experiment. It's the world's first optimized stellarator. I'll tell you a little bit later what what a stellarator is and why it has to be optimized, but I don't want to spend too much, but I just want to give you some idea of what my background is. This machine is located in the Department of Electrical and Computer Engineering. And in fact, there are windows. This is a weird lab. There are windows actually outside the building, and if you can even stand outside and look inside and see the machine. And here's a picture of so I want to give enormous credit to my two other colleagues, Dave Anderson and Simon Anderson. They're not related to each other, but so three of us basically headed this project and got this thing, did all the physics on it, designed it, built it, ran it for many years, and then, of course, all of us got old, and we all retired. And actually, this whole lab, however, since it's the only stellarator of its kind still in the world, the Department of Energy is very clear on wanting to keep this thing operating. So it's still operating, even though it's already been running for 25 years. still doing interesting physics, actually. Here's I just wanted to show you this. This is a cover of the Wisconsin State Journal in 2007. We had designed this experiment to achieve certain accomplishments. For one thing, actually, to get hotter plasmas, because typical other stellators prior to this had very poor confinement, and we fixed that problem basically with this machine. So after we published a number of papers proving that this concept was so much better than other stellators, the Wisconsin State Journal put us on the cover as a first for fusion, which was very nice. So it was nice to see that we got some recognition for this great achievement. And I was going to show you, I just want to show you just some things that are interesting. Here's what the coil looks like that we have on this machine. And you can see this isn't your typical planar coil. This is a 3D magnetic coil. And that's what makes this machine so interesting and gives it all these very specific physics properties. And, and the difficulty with this kind of coil is it's really hard to make. Because, typically if you have a magnet coil, just a nice planar coil, you can just wind this thing in tension, right? You can just go around and wind it and so on, right? It takes no time at all, just like winding thread around a little cylinder or something. But this thing, you can't do that. And so we actually had intended a magnet company to make this for us. But then they went bankrupt trying to do this. So we wound up making the magnets, all the magnets in our laboratory. So here's basically a welding table that we borrowed from Stoughton Trailers. And on this, there's a form in which you take the copper and you sort of hammer it in place and you lock it in and wind a little bit more, lock it in. And eventually you just bake this in epoxy and it forms a nice rigid structure. And the interesting thing too is about the vacuum chamber. This vacuum chamber was explosively formed by American Exchanger Services in Waterford, Wisconsin. Basically means that you have an explosive and you take your stainless steel, you bend it into a form, and you blow it up, and it rams against the form and forms this nice intricate shapes. And this is the physical science laboratory out in Stoughton. I don't know, maybe some of you are familiar with it. Really great engineering place. They helped us build this support structure. And just because it's always cool to watch things blow up, I have this little video here. So let's see if it's only less than a minute. Let's see if this works.
Yeah. We have about 340 grams of charge in there. Here's the form of the die after the blast.
So what you saw in that is that when the charge goes off, there's a huge spray. That's just water. So basically you take this explosive, you fill up the tank with water, and water is incompressible. So if you have a shock coming from the explosion, the water tends to symmetrize the blast onto a piece of stainless steel. And so that's how we got these nice shapes in our vacuum vessel. It was really interesting. American Exchanger, they do a lot of work actually with heat exchangers for nuclear reactors and so on. And they were very happy to to help us make this vacuum chamber. Okay. So why are we interested in fusion? So I'll just go through some of the points that people typically make about fusion, and I'll tell you what some of the problems are. So one thing is right away is that there's an abundant fuel supply. So the fuel for the first generation of fusion reactors will be deuterium and tritium, because that's the easiest fusion reaction to get. And deuterium is really easy to get. It's just heavy water, 1 part in 6,500 of hydrogen and just seawater. So it's essentially an inexhaustible supply. It's the tritium that's the problem. There's virtually no natural tritium in the world. Basically, tritium comes from cosmic rays hitting nitrogen in the upper atmosphere. So you get a little bit of tritium from that. There's some tritium left over from when they're exploding nuclear weapons in the atmosphere. You get now tritium from fission reactors, of course. But there's no pit or mine where you can go in and mine tritium, and tritium only has a half-life of 12.3 years. So if you have a supply of tritium, it's also going to diminish pretty quickly. So what we do is you make tritium from lithium, and this is one of the challenges for the fusion reactors. I'll talk to a little bit about more later. But in the meantime, this supply of fuel is available to all nations. So hopefully you would have reduced conflict over resources. There's, of course, no carbon dioxide or air pollution, nitrogen oxides or sulfur oxides. The ash from fusion reaction is helium, pretty harmless gas. Small risk for nuclear accidents, no meltdown scenarios. Small amount of fuel is actually stored. Has minimal proliferation risks. Reduced hazards associated with radioactive waste. There's no long-lived radioactive waste. There is some radioactivity, obviously from the tritium, but there's more since what happens is the neutrons bombard the first wall facing the plasma, and that activates some of the wall. So there's short-lived radioactive waste coming from neutron interaction with the structural materials. If you play around with different materials, you can somehow minimize some of these radioactive effects. One important thing about fusion is it has a high energy density. So there's minimal land or water use. People, of course, attack solar and wind for the fact that it uses large resources of land and water. I simply, it's hard to get a handle on it in terms of what. So I typically just use the Princeton Net Zero America, because they supposedly this is Jesse Jenkins' group, and they basically went through and tried to say what you would do if you just filled up the United States with wind and solar. And in their case, they only had like 7 to 11% of the US land needed for wind and solar, which is still quite a lot. But so clearly fusion is very energy dense.
I think this is a wonderful statistic. If I may just insert that comment, that last line tells us how phony net zero has become in our language. And of course, that makes no comment also on the duration of the materials for they must last for a long time for fusion as they do for fission, compared with wind and solar, which is so short-lived.
Right. Yeah, I have a tendency to check in on Jesse Jenkins' Twitter feed every now and then.
Good.
Just because, I find him very interesting, and
Yeah.
And I saw him arguing. Actually, he says, somebody was lecturing to him about him. He's basically for everything.
Yeah.
And my very last slide, I'll tell you basically why I agree with Jesse Jenkins, because that you need everything.
Yeah, absolutely.
And that the last thing we should be doing is hitting each other. you
So
know,
true. So
that,
true.
that this is better than this, or,
Yeah.
and so on and so forth. I mean, I think that there's a graph I'm going to show you that I think really brings it out. But hopefully I'll get to that before my voice gives up. But
So,
I think this is the issue. And Jesse, by the way, just even the last few days said he had some disagreement with somebody. He says, man, I am so pro-nuclear. What and he's done a lot actually, especially in the Inflation Reduction Act. He had a big part of it to keep fission reactors running, right? There's money in the IRA to keep fission reactors running. So he said, some of that was actually due to him. So,
right.
but I'll show you when I get to the end.
Yeah.
Why I believe that. So why aren't there terrestrial fusion reactors? At the last minute I put terrestrial because somebody will say, "Oh, we have a fusion reactor. It's out there in the sun," and we all know that. But basically, this is a hard problem. And let me just say personally, from my experience, I went into this field like in the 1970s, and I thought by the time I was ready to retire, that I'd be living in a very different world, that there would be fusion reactors all over the place. And it's astonishing to me that there are not fusion reactors. And I think is because it's a hard problem. And I got a good feel in my career for exactly why it's such a hard problem. And one of the problems, of course, is that you got this hot gas. It's much hotter than the center of the sun. How do you confine this gas? How do you keep it? You can't obviously put it into a metallic container, it'll just melt the walls. So we keep that gas in with magnetic fields. But then the gas leaks out, hits the walls anyway, and stuff comes off the walls, cools the plasma, and then it just cools off and burns out. The hardest thing in a plasma is keeping it going. So presumably you know what a plasma is. A plasma is ionized gas. So the
Yeah.
electrons and ions are separate from each other. They form this sort of mixed fluid that has not only the properties of a fluid, but because the ions and electrons are separate, it has very complicated electromagnetic properties. And the killer of plasma is what's called turbulence. So you see turbulence, like in smoke rings or, anyway, one of the big achievements of the field actually in the last 20 years especially is really getting an understanding of turbulence with very complex three-dimensional codes and starting to deal with trying to avoid, how do you avoid turbulence? It's a huge accomplishment, but it gets almost no press because it's just the hard work of understanding rather than getting a big fancy result. There are problems of getting new materials. And the phase of fusion that we're at is to finally to get more fusion out than it takes to create and sustain the plasma. And I'm going to go into that very carefully. So let me just talk about the easiest fusion reaction is to combine deuterium and tritium. So this is what most of the world is working on. So basically you have deuterium and tritium, these are deuterium, tritium, both isotopes of hydrogen. So deuterium has an extra neutron. Tritium has two more neutrons. So if you fuse these together, and they're about 150 million degrees, they form helium and a neutron. The helium has 3.5 MeV of energy. MeV, an electron volt is a standard unit of temperature that we all use. A way to think about it is 1 EV is 11,600 degrees centigrade or Celsius. So 11,000. So, you know, typically if you just want to get a feel for what it is in Celsius, multiply it by 10,000. So you have 3.5 million electron volts, and then multiply that by 10,000. You'll see basically what temperature that is at.
Got a quick question. Is there any point in mentioning beryllium in there with the lithium, or is that just a thought?
No, well, you can't.
I thought that would stabilize it if you added beryllium to the lithium.
Well, I'll tell you where beryllium. Well, beryllium is actually in a very key importance in this second reaction down here.
Yeah,
Pointing with my finger,
that's
realizing.
what I meant. Yes, there.
Yeah. So what happens is, yeah, that's a great point actually. So what happens is one of the things you absolutely need to do in a fusion reactor, and this has not been demonstrated yet, that you need to breed your own tritium. You can't go off on the market, and I'll talk about that a little bit more later. But you can't go off and just buy your tritium. You need to make it in-house.
Okay.
And the way you make it is you take this neutron, and there's some lithium blankets outside. Here's the plasma. Here's the plasma, and outside there are some blankets. And the neutron comes in, hits the lithium. This is lithium-6, by the way. So most lithium is lithium-7. You need lithium-6, and it converts into helium and tritium. And then you need to go back and recycle your tritium and put it back into the plasma so that you have a closed fuel cycle. So what Richard said very nicely, what beryllium does for you is a neutron multiplier. So basically, you take this neutron, will come in, hit the beryllium, and then you'll get like 2 neutrons out, and
Okay.
you vastly improve your breeding of tritium through the use of the beryllium. The other way, actually, beryllium was being used for a long time was to coat the walls of the fusion experiments. I don't want to call them reactors, but their fusion experiments was coated with beryllium because it could withstand some of that heat. But the big decision of the ITER project that I'll talk about later was they scrapped all the beryllium. They said it's too difficult and stuff, and they all went to tungsten. So right now the plan is beryllium is needed here as a neutron multiplier, so we can breed enough tritium. Tritium basically costs like $30,000 a gram now, but there's so little tritium in the world. Okay, here's a point I wanted to make. Actually, I had talked about this a little bit with Richard at one point, which is this is a self-sustaining reaction. People sometimes don't understand that about fusion, which is I think you keep having to put energy into the system and you simply just like a gain multiplier. Basically what happens is this helium, it's trapped in the magnetic field. It's at a very high temperature, and it deposits its energy back into the plasma, and keeps this reaction going. So basically, you need heat from an external source to get the temperature up to 150 million degrees. But once you start forming fusion, once you start forming fusion, the helium that's produced stays in the plasma and heats it up, and you have a self-sustaining reaction.
Can I ask the units of the temperature? Is that Celsius or Fahrenheit?
So this is, like I said, this is millions of electron volts, and 1 electron volt is 11,600 C.
So it's all C, or this
I'm sorry?
150 million
Yeah, 150,
temperature
right.
is
So
all
I'm
C.
sorry, I'm
It's
sorry.
all C.
You were looking right. Exactly.
All this stuff is C.
Yeah.
Look, we're the only people over here who use Fahrenheit.
Yeah, I never use Fahrenheit. This is
Yeah,
right.
well, it's a concentrated. It's
Yeah.
much higher.
So
But
this,
I just read an article that some company, and I can share it later, got a plasma up to 400 degrees, I thought it was C, for 48 hours. I mean, that's 400 million. I mean, it's way beyond the 350, the 150 million.
which company do you know?
I'd have to get out of the screen and find it.
Later
I
in my
say,
talk, later in my talk, I'm going to trash a whole bunch of companies. So we'll
I'll find it.
save
I'll
that type
find
of
it.
list.
I'll
But
find it on my phone.
yeah, this is yeah, right. You're right. So this is this is like on the order of 14K, 14,000 electron volts, 150 million degrees Celsius or so. So right. So it's like an optimal temperature which you want for this DT reaction. This actually isn't even the hard part, to tell you the truth in all of this. Here, let me go on. So this is sort of nice. People like this. Basically, you get the deuterium in 40 liters of water. You got these 4 buckets here, 1 liter, 10 liters each. And you take the deuterium out from that. It's like, 1/6000th of the water, plus 5 grams of lithium is equivalent of energy of the 40 tons of coal.
Impressive.
So, I'm sure you see all this, of course, with fission reactors, but
Yeah.
lithium is also very abundant, but the breeding this fission tritium in a fusion reactor has not been demonstrated yet, and I wanted to emphasize that. It doesn't, that's a huge challenge that a lot of people don't make clear, actually. I wanted to talk, let's see. So why is fusion so hard compared to fission? I just wanted to briefly go through some of these slides, hopefully not spend that much time on it, but maybe it's informative for people who aren't familiar with fusion or what the problems are. So you have your standard fission reaction, right? Neutron comes in, splits a uranium into krypton, barium, and so this is actually easy. This is so easy to do. Because basically your neutron, you basically want in a thermal energy anyway. And why is that? Then that's because it doesn't have a charge. The neutron doesn't have a charge. So it can come in, hit the nucleus, get absorbed in and break apart the uranium so easily. The problem with fusion is you have these nuclei which are positively charged. So you take these positively charged nuclei and you bring them together. What happens? They don't want to combine. They want to repel each other, right? There's a repulsion between these 2 nuclei, and this is sort of what I'm plotting here. That as they get closer and closer, the force between all these protons in the nuclei increase and just want to push them apart. So what saves you in all this is what's called the strong force. I think the strong force comes in like, I always get this wrong, but it's something like on the order of 10 to the minus 24 meters or so. If you can get them closer, around that, in that distance between them, then the strong force takes over and then pulls the protons together with the neutrons, right? So you need to overcome this barrier. What we call a Coulomb barrier, that these 2 positively charged nuclei just want to repel each other, but you want to get them, if they can get close enough, then the strong force takes over and then they combine together. So, is that clear? Hopefully.
Yeah, that's cool.
There's a little bit of quantum mechanics in this too, because it doesn't really actually have to get over the hump. Gamma did this basically. It can just basically just tunnel right through this barrier too, but that's a whole nother subject that I didn't want to get into. So here, I'll go through this hopefully quickly. This is pretty standard for fusion and fission. I just sort of wanted to draw out the commonalities between these 2 methods of making energy. So it has to do with, it's binding energy. So what's binding energy basically? So you have a nucleus, for example, And say you want to strip apart all the protons and neutrons in the nucleus, right? That takes an enormous amount of energy to split them into neutrons here and the positive protons. And what you find from this is that the mass of these individual nucleons is much greater than the mass of the nucleus. So what happened, right? So this is called the missing mass, basically. So the missing mass, just as we all know, comes from equals mc squared. If you have if this is missing mass compared to this sum, that missing mass goes into binding energy that keeps the nucleus together. So here's a plot. This sort of unifies fusion with fission. This is a plot of binding energy per nucleon. Here's the number of nucleons in the nucleus. Here's uranium-238 out here. Here's hydrogen. Hydrogen is over. Sorry, deuterium's over here. Hydrogen actually would be over here at 0. It zero. It only has one proton, so you don't need binding energy. It doesn't have to stick with anything else. But now you have a proton and a neutron. They have to stick together, so that requires some binding energy. And tritium requires some more. So this is basically binding energy per nucleon. And as you see, and this is basically what the sun does. The sun starts out here with hydrogen. It works. Oh, sorry. It works its way up to here, up to iron. So iron has the most binding energy per nucleon. Iron is the most stable element in the universe. And basically what the sun does is it works its way up and creates all these, not our sun necessarily, but other suns will work its way up and create every element up to iron. And that's it. Then it'll stop. But fusion doesn't work anymore beyond iron. And what happens is, if you want to get all these other elements, this is where supernovas come in. So there's an extraordinary amount of energy that creates everything beyond iron comes from supernovas. And everything, of course, that we're made of and everything in the universe is made of all the elements that come either from the fusion or from supernovas. So here's the one thing I wanted to show you is that, see, this is helium-4. We were talking a little bit about this helium-4. Look how it's, so as you get up here, the more binding energy per nucleon, the more stable that nucleus is. So helium is a very stable nucleus. It has a very high binding energy. And it's one of the reasons why, for example, if you look at the decay of uranium down here, as we talked about too, the different ionizing radiation, you have beta and gamma rays, and then you have alpha particles. And alpha particles are just these helium nuclei. And most of the, a lot of the radioactive decay comes from, it's so stable that it naturally forms, and it's kind of like somebody just spinning off these very stable nuclides as uranium will decay back towards iron or so. So fission, what happens is, so fusion occurs here, combining these lower mass elements into these heavier particles, and uranium goes the opposite way, but it's all trying to reach basically the peak in the binding energy, the most stable basically being iron. So fission works this way by breaking elements apart. Fusion works this way by trying to combine nuclei together. And it's this steep slope here in fusion that you can see. So you have, here's deuterium, here's tritium, they're going to combine and form helium. This steep slope here is what makes fusion more interesting even than fission. And I was going to put this up here. I'm not going to go through it, but for anybody that's interested, come back and look at my slide. But so if I define energy density as the energy released per unit mass, I just went through a little calculation just to show you what happens. With fission, you have a neutron impinging on uranium, splitting it apart, giving krypton and barium, basically using the binding energies of these different nuclides. And then I'm working myself down, basically, see what 1 gram of uranium, for example, you can get from 1 gram of uranium, you can get 20,000 kilowatt hours of energy. So you do the same thing on fusion because of that steep slope. So on 1 gram of fuel for a DT reaction gives you 200,000 kilowatt hours.
Impressive.
So fusion gives you 10 times the energy density than fission does. It's one of the reasons why people are interested in fission. I'm sorry, in fusion, including some of the properties that I mentioned.
That's a wonderful table. Thank you.
Yeah, so you can look through it. It's pretty simple, just Avogadro's number and so on and so forth, and the binding energies. You can get all this, but I didn't want to bore just by just going through this, but I thought it's just worth showing it. You can look at it later. And if anybody has questions, you could ask me. But so we'll get to this guy in a second, but I just wanted to explain cross sections. I'm sorry if this talk is a little technical, but I can't explain things about fusion without being technical, because otherwise it's just your standard talk about fusion, about all the great things about it, and I can't tell you what some of the problems are without being technical. So I apologize for some of the technical aspects, but I wanted to give a realistic view on what fusion is. So cross-section basically tells you, what the probability of some reaction occurring. Think of it, and it has these nice units actually of barns. So think of it like this. So think of it like say like I'm standing in front of a barn and somebody's blindfolds me and gives me a ball and spins me around and tells me to throw a ball at the barn. And hopefully if I'm in the right direction, it's probably really easy to hit the barn, right? So barn has a huge cross section. So that fact is that it's easy to hit that barn. But now somebody says, okay, I still have that blindfold on, I want to hit this window. So what's the probability actually, if I'm blindfolded, that I'm randomly throwing my ball at the barn, but I'm actually going to hit a window? And the window is a much smaller cross section, right? So probability that I'm going to hit that window is going to be much smaller. So that's basically what I'm showing here, is that this essentially tells you what the cross sections, what the probabilities are for DT fusion over DD fusion. So DT fusion is, you can see the cross section is at least factors of 100 higher. So the probability of having a DT fusion over DD is at least 100 times more. But here's the thing that I wanted. There's a thing called basically that if you just try to smack two nuclei together, maybe there's two deuterons or a DT or a nucleon and so on, most likely they're just going to scatter. And that's what this means, Coulomb scattering. They're just going to come together and just let's say if I can put this here, come apart and just leave, right? They're not going to fuse together. So you could see here that how much higher the cross section or the probability is for just scattering. And what this means is you can't just have like two beams colliding with each other and expect to have a fusion reactor from that. You have to have it in some sort of confined plasma so that you can have many more ions. You have to have the ions confined for many scattering times, so they can scatter, say scatter 10 times, but come back to each other, and maybe the 10th time, maybe then they'll fuse. That's the difficulty of fusion, right? You have to keep the plasma together so that they scatter many times and then fuse. So anybody know who this guy is?
No.
No.
He had to do with television.
Ooh,
No.
cathode ray tube.
Huh?
I don't know.
helped develop television.
Oh, wow.
Spitzer?
Huh?
Is it Spitzer?
Oh, no, not Spitzer, no. This is but Spitzer's a great name though. This is here, Philo Farnsworth.
Oh, yeah.
Yeah, so Philo Farnsworth, who's a guy made really incredible gains in terms of developing television. He invented this thing called the fuser, and this is him standing next to this fuser device, which, the thing that Farnsworth did, right, is he really tried to understand how to focus electrons, onto like a screen or so to invent television. So he applied this to fusion, actually. This is back in the 30s or so. Um, and I just find it kind of amazing that this guy was so farsighted that he would think of this problem. And you can make fusion this way, but the problem is that, as I just talked about, what happens is if you're trying just to accelerate these deuterons into some other gas of deuteron, the probability is they're just going to scatter. Maybe you'll get one or two fusions for every, 100 deuterons that you put in there. So you'll get some fusion out, but mostly they're just scattering, they're lost. But this guy, Philo Farnsworth, thought about doing this back in the 30s, which is really kind of astonishing to me. Anyways, here's another picture of so if I take this cross section sigma and I multiply it by the velocity. So this is actually an area. So imagine that this is like the area of a circle. And here's a cylinder. So velocity is just length divided by time. So basically what happens is reactivity is a measure of like how much volume this particle will go through in a given amount of time. And if I knew what the density of this other species was, right, I'd know how many particles were in this volume. And so basically you get an idea of how many reactions per second you would get. So that's what sigma v is.
Quick question. When you said of a circle, you meant sphere?
Well, actually a circle. So sigma is actually an area.
Okay,
So so I meant this
sphere.
I meant like a cylinder. So
Well, you did mean a sphere, cylinder. Okay.
like
You're
a
thinking
cylinder.
2 dimensions. All right.
But the 3 dimensions comes in through the fact that it's moving, so it traces out like a cylinder.
Okay.
Right.
I got you now.
Yeah. So this is a plot of the reactivity as a function of the ion temperature. And again, this is in kilovolts. So to get this in in Celsius or so, just multiply it by 10,000. So 100. So 100 is what? It's like I think a billion, right? It's like I think a billion Celsius. So dt. So you can see from this that dt is deuterium tritium. This curve here has the highest reactivity. It's the easiest thing to do. Oh yeah, here I finally actually showed you that 1 electron volt is 11,600 Celsius. You don't need to be at the top of the peak, but most envisioned fusion reactors will be occurring around here. I'm sorry, around here, like around 15 kilovolts or so, which is on the order of 150 million degrees Celsius. The core of the sun is only 15 million degrees Celsius. So the temperature of plasma is going to be 10 times hotter than the core of the sun.
Oh,
And this has already been done. I mean, this has been achieved like years ago. So that's not the hardest problem here. But you do, what you get from this is that you need to keep this hot plasma away from the walls of any container, and you do that with magnetic fields. So here's some of the other fusion reactors that people are thinking about. So the other one is D-helium-3, which is this red curve. and then DD reactions and so, and then there's one people really like P-boron 11 and so on. Let me get to this. So I basically just wrote this out again. I guess um, the point I wanted to make is that there are a whole bunch of startup companies, and I'll talk about more of them in a few minutes. How are we doing on time? Oh, what time did you want to end, Richard?
Oh, we don't have a deadline until noon or so, but it's fine to go over a bit to 11:30 is typical,
Okay.
but we don't have to go that long either.
Well, yeah, unfortunately, yeah, okay.
You've got a voice to contend with, so you're doing fine.
Okay, all right. I'll leave this, try to go a little bit more, but you know, this guy Harrison Schmidt's an interesting character. I met him a number of years ago. He's an Apollo 7. He was like the only scientist that was ever walked on the moon. He was a professor, visiting professor at the UW for a couple of years. He was a geologist. He has a PhD in geology. I think he was also the senator from New Mexico at one point. Um, and he's the guy who promotes mining. I say there's this fusion reaction here, dihelium, helium-3 with deuterium. And the problem with helium-3 is that there's almost no helium-3 on the Earth. But the moon is full of helium-3, and that's because it comes from the solar wind, and the Earth's magnetosphere keeps the helium-3 actually from piling up on the planet. But the moon doesn't have a magnetosphere, so the moon is just full of helium-3, which is what the Apollo astronauts found. And so this guy is still around and kicking, and he's got a little company called Interloon, which promotes the mining of helium-3 on the surface of the moon. This is their little buggy that supposedly they're taking the regolith on the moon and warming it up and extracting the helium-3. These reactions are favorable because if you ever can get to something like this, then there's no neutrons to activate the walls. There's no radioactivity at all. Actually, that's not quite true for this reaction, but if you could ever get to P-boron 11, then there's no radioactivity at all coming from anything, and you could just make electricity from the charged particles that come out. So startup companies are looking at all of these different fusion reactions. All right, so let me see if I can get through some of these quicker. You confine this plasma in a magnetic cage. So if you take this magnetic cage, most of the experiments are in the design of what's called a torus that looks basically like a donut or a bagel. It has two magnetic fields. There's a magnetic field that runs around this way, the long way in your bagel, called the toroidal direction, and there's another field that goes around this way, the short direction, called the poloidal field. And this was known back in the 50s. I think it was even Enrico Fermi who pointed this out, which is that if you only had this toroidal field, the plasma wouldn't stay in this configuration. They would just drift right out. And to think of this, it's you might have all played around with honey dippers at some point. So you take your dipper and you put it into a pot of honey and you pull it out, right? What's going to happen if it just drips down, right? And so and so what happens is if you want to keep the honey on the end of your honey dipper, you start twirling it, right? And you can make it horizontally, and if you twirl it, you can keep the honey in the grooves of this honey dipper. And the reason why is because here, if I'll go on my screen, the honey will start to drip down, right? But if you twirl it up fast enough, that drip will come back up again. And then when it falls, it'll fall down onto the honey dipper, right? So if you can twirl this thing, that motion of gravity to pull it down, if you bring it back up again, it'll fall down, and you can keep that honey in there by just keep twirling it. And then when you want your honey, you could stop twirling it, and then the honey will drip down. That's exactly, pretty much exactly what happens in a magnetic confinement device, that you need this twist in the magnetic field to keep the particles stationary. This So I wanted to explain the difference between a tokamak and a stellarator. The difference between a tokamak and a stellarator is how that twist in the magnetic field comes about. This is an important concept, actually. For tokamak, that twist comes about because the plasma current, you have a transformer that runs down the center of your tokamak, and you pulse it, and the plasma current acts like the secondary of a transformer. So you have a current that's induced in your plasma that runs around the long way in your donut, and basically forms a magnetic field that goes around the short way. So that colloidal field is created by the current running in the plasma. In a stellarator, that twist is caused by magnetic coils that are outside the plasma. And this is what I've been working on my entire career, is a stellarator. And the problem with the problem with the tokamak is, because you have this current running in the plasma, it can drive a number of instabilities. And this is a key difference. These instabilities don't show up in stellarators. But the tokamak is the leading fusion concept in the world today. And I would just call out, actually, the fact that the tokamak was actually invented in the Soviet Union. Most people would recognize Andrei Sakharov, the inventor of hydrogen bomb, won the Nobel Peace Prize, I think in the mid-70s. He was one of the he and Igor Tamm invented the concept of the tokamak in the 50s, and Lev Artemovich actually built the laboratory that built some of the world's first tokamaks. And the amazing thing is that in the 60s, they reported results that people were absolutely astonished by. They couldn't believe it. They reported such a hot plasma, that the plasma was so hot, and everybody dismissed it, thought it was just Soviet propaganda and so on and so forth. So a British group in the 60s took a laser, and a laser was a sort of a new concept at the time, took a laser and measured the temperature of the plasma in the Russian tokamak, and said, you know, these guys are right. This temperature is exactly what they said it is. And so everybody started building tokamaks after that. It was sort of a key moment in the development of fusion, of how well this tokamak was heating up the plasma and working. In contrast, the stellarator was invented by a guy named Lyman Spitzer. And Spitzer was also a brilliant guy. So, you know, the legend is, and I think the legend is true, is that he was an avid skier and mountain climber, and supposedly he thought of the whole concept of stellarator on a ski slope. And by the time he got down, he had thought about some of the essentials of how to build a stellarator. So he's the guy who basically set up the Princeton Plasma Physics Laboratory, and started some of the fusion program here in the United States, and built some of the first stellarators. And this, as I said, this is what I've been working through most of my career. Spitzer, of course, is also the guy who came up with the concept of the Hubble telescope. So if you ask an astrophysicist who Lyman Spitzer is, they say, oh yeah, he's a, great astrophysicist. But if you talk to a plasma physicist, they say, oh, Lyman Spitzer, he's a great plasma physicist. So people in different fields look at him as a brilliant mentor in each of their fields. I'm going to go through this fairly quickly because I don't want to spend too much time of it, but I thought it was important to point out for people who don't know that Madison is a leading site for fusion research and development in the United States. So if you don't get too much out of this talk, at least appreciate the fact that there is a lot going on in the city and in the outside surrounding area on fusion. So if you look in the United States, I would say fusion and maybe Boston are probably the hubs of the fusion world in the United States. There's a diversity of experiments throughout this area. There are three experiments. And these are just major experiments. There are all sorts of smaller plasma physics experiments, but I just picked out the three larger ones. There's a stellator helically symmetric experiment, our experiment in electrical engineering. There's a reverse field pinch called the Madison symmetric torus, which is in the physics department. There's a spherical tokamak called Pegasus, which is in the engineering physics building. And then there are three private companies that spun off from the university. So there's Type 1 Energy, which is basically wants to build a stellator based on a lot of what we discovered with the helically symmetric experiment. There's Rialto Fusion, which is in Stoughton, where the physical sciences laboratory is. They're working on a mirror machine. And then there's a company called Shine Technologies in Janesville that does a lot of neutron sources, medical isotopes, etc. Let me try to go through this quicker than I wanted to. I was going to just say this about what's interesting about the experiment we built. Here you can just see a nice picture of the vacuum chamber that we made through this explosive forming. But the amazing thing about this machine is that this shows you contours of constant magnetic field, and in our machine, and it's the fact that we can make this kind of contour is what gives this stellator its incredible characteristics. Basically, this is a machine that we could have only built. We started designing this in the 90s, and we were only able to do this in the 90s because of the vast improvement in computer power at the time. And so we were the first to actually design a stellator from the inside out, basically saying, we want a stellator that has this property. What do the coils have to look like to make this property? Let me go on to the reverse field pinch. Basically, this is an incredibly interesting experiment where there's a reversal of the toroidal field at the edge of it. This reverse field pinch, it has much smaller toroidal field than other experiments, and because of that, there's a lot of instabilities that occur. Madison symmetric torus has done a real bang-up job of understanding the instabilities in this plasma and then trying to fix them by tailoring the current profile. And there are these like tearing modes where the magnetic field tears apart and reconnects. So it has a lot of applications to astrophysics. There's the Pegasus spherical tokamak, which basically spherical tokamak is a tokamak, but rather than looking like a donut, it looks more like a pear shape. So you have this very thin center stack in the core, and basically what you want to do is even get rid of that center stack completely, but you still need to drive current in it. So their main thrust is, how do you drive current in this tokamak without using the transformer? Type 1 Energy, as I said, is using high temperature superconductors to try to make a scale up of some sort of like HSX type reactor. They actually recently announced plans to build a prototype in the Bull Run fossil fuel plant in Clinton, Tennessee, in collaboration with the TVA and Oak Ridge National Laboratory. However, this is mostly an engineering experiment. They're not going to generate electricity or use tritium, but it's just to understand whether they can build stellarator coils with high temperature superconductors and also use advanced manufacturing to help ease one of the problems with building stellarators. It's really difficult to build it. So hopefully advanced manufacturing capabilities can aid in building stellarators. This just got a lot of press this summer. There's WHAM experiment just achieved its first plasma in July. It's located in the Physical Sciences Laboratory. This has a 17 Tesla high temperature superconducting coil, which they got their coil from Commonwealth Fusion Systems, which is in Boston, which I'll talk about in a minute. This is the high temperature superconductor right here. This mirror machine is like an old concept from the 70s, 60s through the 80s. This whole program was abandoned in the 1980s, but there's some new ideas on how to stabilize the plasma with improved technology. Some ideas of how you stabilize it and how you and the fact that you could use these incredibly high field magnets. So this is one of the startup companies again. And the last one is Shine Technologies in Janesville. Very interesting company. They're not planning to do fusion until much later, but they're using fusion now for things like radiation hardening, making isotopes using fusion neutrons like lutetium, right? Is that how you pronounce it? Lutetium-177 for cancer treatment. They already have a facility now. They're taking orders, I think. Then they're looking at recycling and reusing spent nuclear waste using fusion neutrons. And then later on, they'll probably get to fusion as an energy source. So here's they actually have this thing called FLARE, Fusion Linear Accelerator, for looking at radiation effects, and they have one for making isotopes too. So using it for neutron source. Okay, so anyway, so hopefully you get some feel for what's going on around Madison, that this is really an exciting place to be. So
this Shine company was involved with a company on the West Coast that got that high temperature, close to 400 million degrees. They were tied in with them in some way. And I can't find the name of that company.
Well, if you have some information about it, send it to me. But I don't think we really do anything with fusion right now. I think they're really concentrating on just making commercial products. Actually, they're very successful company. They're really getting a name for themselves, from what I understand. Okay, good. So let me get into some of the things. Then I have to get into, unfortunately, some definitions here. So I wanted to talk about this quantity Q. So basically, there's a term called scientific Q. So scientific Q means you get energy out from fusion. It's the ratio of the energy out from fusion from the energy input for heating. So you want to heat the plasma up to this 150 million degrees Celsius, and you'll get an enormous amount of fusion energy out. So the question is, what is this output energy divided by this input energy, right? So if they're equal to each other, that's called scientific break-even. So this is the goal for all fusion devices, and it's never been achieved yet in any magnetic fusion device, but it's close. But it has been achieved within the last few years using laser fusion. So that's in 2022. when you saw the entire, for the few days or so that your newspaper had these headlines about big fusion breakthrough and so on, that was having to do with the fact that it finally got scientific break even using laser fusion. If you get up to Q roughly greater than 5, this is what's called a burning plasma. So that means, as I said before, what happens is fusion occurs, you get this very energetic helium ion, and it deposits its energy back into the plasma. We've already had experiments actually where some of the helium does heat the plasma, but we've never gotten to the point where the plasma heating from the fusion alpha particles equals even the energy input from external heating sources. But if you can get up to Q equals 5, you have what's called a burning plasma, so that the helium is maintaining the hot temperatures in the plasma. So if you can get above 5, and the reason it's 5 is because the amount of energy from the helium is 1/5 of the total energy out. So that gives you another factor of 5 that you have to achieve to get what's called a burning plasma. All right. The next thing I wanted to show you, I'm sorry, is you can get a Q scientific of infinity. So what I mean by that is that Q scientific being infinity is where this energy input for heating, this thing right here, goes away. You don't need it anymore. So what happens is, so you see that this is just missing right here, and that the fusion output from the helium is just deposited in the plasma and keeps the reaction going. So that's Q scientific of infinity. All right. So then I want to talk about Q engineering to say, okay, this is just the energy, input into the plasma, but to make this energy input and to keep the plasma going, then really what you should be doing is talking about, what all your facilities is, what's the power that you're taking out from the wall plug, right? Because otherwise, it's a little distorting just to pick Q scientific. It's not meant to be distorting at all. There's a clear goal in plasma physics to get to Q scientific, but it's mixed up a lot in the press and very misleading, unfortunately. But it's a clear difference between Q scientific and Q engineering. Q engineering would more tell you what the power needed or the energy needed to run your facility. And you need this to be far in excess of 1 to actually have a fusion reactor. We're not even close to this in fusion. And then the last thing is the Lawson criterion, which basically says you basically need to have a plasma density high enough, at high enough temperature for a long enough time. So the product of these three has to be above this quantity. This basically, Lawson is a guy with this back in the 1950s, is still true. This gives you a figure of merit if it tells you how close are you to ignition for your fusion reactor. So here's a plot of what this triple product is as a function of time. And in this chart here, so this fusion product actually made tremendous progress all throughout the decades of fusion development, and then kind of stopped and petered out. But in this graph, they wanted to compare it to Moore's law, number of transistors that you could put on a computer chip to show that the progress of fusion was making was comparable to the progress computer chips were making. And the problem is that once you get up to here in fusion, then you need bigger and bigger machines. They're harder and harder to build. They're more expensive. They take a long time to build and so on. This is just tokamaks, by the way. So tokamaks are the leading fusion concept. In this graph, it shows you the triple product as a function of temperature for a large range of different devices. And here, this is the curve here for laser fusion, this black curve. And here this shows that this laser facility called the National Ignition Facility, NAF, actually went beyond ignition in their experiment from 3 years ago. So they're the only people right now to have gotten into actually ignition. And these are just machines that are being planned to be built in the future. I wanted to show you this, which is there was that headline that was a couple of years ago that the most energy out from any fusion device, including the laser, was that the energy from fusion was 69 megajoules. Well, that may sound like a lot, but it's not at all. It's the average home uses 100 megajoules in a day. So the amount of fusion power, or fusion energy actually, that you got could just run one home for one day. So to put this in perspective, but it was an enormous accomplishment at the time because nobody had gotten up to could even make this much fusion power. So for a magnetic fusion device, the highest Q scientific was actually achieved way back in 1997 in the same machine, JET. They got a Q scientific of 0.67, not quite 1, but close to 1, which to this day is the highest ever achieved in any magnetic fusion device. When they ran this is their shot, which ran for 5 seconds in JET a couple of years ago. Then they got their 69 megajoules. Q scientific actually dropped down to 0.33, which they didn't mention in a lot of the news articles. And the reason is because they changed what the wall of the machine was. This machine here had a carbon wall. This machine had a mostly tungsten wall. And the problem of using tungsten is what it tends to radiate a lot and so loses a lot of energy. So even though this is a great result, the real disappointing aspect of it is that the Q scientific actually dropped for this experiment. All right, so I just want to talk about okay, I think I'm doing okay. This National Ignition Facility, it's the only lab that ever surpassed fusion break-even and even got to ignition. So what did they do? They have 192 lasers. They delivered 2 megajoules of energy in about 5 nanoseconds. Nanosecond is 1/1000th of a second. So if you think what that power is, that's 500 terawatts of power in that incredibly short time. So the entire world uses, I think, like 20 terawatts of power. So this is over, 20 times the world's consumption of power for that 1 nanosecond. It's an incredible amount of power. But what it does is it takes these 192 lasers and it focuses on this, what's called like an X-ray cavity. It's called a horum, and it's made out of gold and depleted uranium. And it shines, there's a little capsule of deuterium and tritium in the center of this, but the lasers don't shine on the capsule. It shines on the walls of this horum made out of gold and depleted uranium. And these walls, once they heat up, they give off X-rays, and it's the X-rays that then implode on, which then focus on this shell of deuterium and tritium. And then the shell explodes. And when the shell explodes, basically, the rest of the capsule, there's an implosion of the capsule itself inward, which raises the density incredibly and raises the temperature of the plasma inside to thermonuclear temperatures. And then that's when you get a fusion reaction. And that's what they were able to do in this National Ignition Facility. So here's just, so this is actually just a chart basically there's 5 shots that they took that were interesting for the last 3 years. So just saying that there's 5 shots in the last 3 years just tells you the practicality of laser fusion being a fusion reactor,
Nice.
which is that basically, so here they took, so the first shot that made all the news, they had roughly 2 megajoules of power of energy on the capsule. I'm sorry, on the laser output, not the X-rays, but the laser output was 2 megajoules, and they got 3 megajoules out. So for a Q scientific of 1.5, so they actually exceeded that Q. Now the highest Q in any fusion device is now 2.4. So they got this, for example, 2.2 megajoules of laser energy, and they got 5.2 megajoules out. So here's what I want to focus on, or dwell on for a second, just so you can understand really the significance or possibly the insignificance of this result, which is the facility itself uses about 4 megajoules to operate these lasers. Okay, so it's nice to have a Q scientific, energy input, energy out, but the whole lab itself takes 400 megajoules, right? So if I want to say what the Q engineering is, I have to take that 5.2 megajoules and divide it by the 400 megajoules. And now my Q is only, less than 100th. You can't operate a fusion reactor, right, from that, right? So the difficulty of all this is that the lasers are so inefficient. There's basically a 0.5% of efficiency in the lasers. Nowadays, you can get 10 to 20% efficiencies in lasers, but in a power plant, you want 10 shots per second. The National Ignition Facility, there's so much time and effort just to set up the shot and take your shot. It takes maybe 1 shot per week rather than 10 shots per second that you want in your reactor. 1 shot per week, maybe they can get it down to 1 shot per day. The targets are incredibly complicated, expensive, and fragile. All I'm just trying to say is that you can't get a fusion reactor out of this, even though they made a nice scientific achievement. But I wanted just to focus real briefly on this.
Yep, go ahead.
Go ahead. The mission of the National Ignition Facility really isn't laser fusion, it's stockpile stewardship. So the funding comes from the National Nuclear Security Administration, which manages the nation's stockpile. The US stopped did underground testing in 1992. And shortly afterwards decided that, they're going to set up facilities for computational test beds and experimental facilities to assure that nuclear weapons were reliable. So that's basically what National Ignition Facility mission really is to make sure that the arsenal that we have is up to date, working properly, functional. What's interesting is when there was a huge announcement about the achievement of the National Ignition Facility, I thought it was the thing that struck me was that there was an NNSA administrator named Marv Adams who spoke. Secretary of Energy Granholm spoke at this news conference. And his statement was, it underpins the credibility of our deterrent by demonstrating world-leading expertise in weapons-relevant technologies, which I thought was a nice way of saying what the real mission of NIF really is, not really so much fusion per se. So I was just gonna, without getting into political discussion, I would just raise these issues, which is, will the research at NIF lead to improved capabilities for nuclear weapons program? Is this something that we actually even need or desire? And is the NIF facility itself stabilizing or destabilizing to current nuclear postures? So I just raised those questions and without necessarily getting through a deep discussion about that right here. But point that out that this facility itself isn't going to lead to fusion reactors, and that's real program mission is stockpile stewardship. So then I want to talk about the national, I'm sorry, ITER. So where do we go from here in terms of real fusion reactors? So what the world was relying on is this monstrous experiment being built right now in Cadarache in France. This is like 30 meters high. It weighs about 23,000 tons. Its goal was to inject 50 megawatts of heating power into the plasma and obtain 500 megawatts of fusion power out for up to 10 minutes. So that's a Q of 10. So this would be this would have been the first fusion experiment where you get a Q greater than 1, actually even greater than 5. And so this would be a demonstration of a burning plasma in a magnetic fusion experiment. And I emphasize
Were they delayed by a recent fire, or is that just phony?
not a fire. Actually, I'll tell you exactly what the problems were in a
Okay.
second.
Sure.
It's like in the next slides.
Okay.
But, let me just get that. I would emphasize this is not a reactor. It's a science experiment. And it's a science experiment specifically because we've never had a plasma really where the alpha particles are depositing all that energy in the plasma and heating it up, and we don't know for sure if there are going to be instabilities that are driven or what's exactly going to happen. There's a lot of computational models, obviously, but this machine is not going to generate any electricity at all. It's an experiment, but it's a joint experiment from Europe, China, India, Japan, Russia, South Korea, and the United States.
Yeah.
I'm going to show you, I'm going to skip this slide. I just want to show you actually that ITER, which means the way in Latin, actually was a product of the perestroika period where Reagan and Gorbachev met in Geneva in 1985, and they set the motion for this massive experiment to be built. So ITER was supposed to have gotten first plasma in next year in 2025, and then not use DT till 2035, and then that just got pushed back. So it won't make first plasma till 2034, and then they'll use DT in 2039. And in Richard's question right here, the problems with ITER was this: the vacuum vessel was not built to tolerance. So when they got all these pieces of vacuum vessel together, and you have to weld them together, they wouldn't weld together. So they have to go back and reform some of the pieces, or basically get the vessel back into tolerance so that you can weld all these sections. This is an enormous issue. That's some of the thermal shields were cracked due to improper welds.
Hmm.
I mean, the fact that you don't do the welds correctly. They used a crappy welding company, which didn't have quality control on their welds, and it kind of reminds you a little. What was that vision company, New Star, that made some? I mean, these are the kinds of things that creep up, right? If you don't keep track of quality control. So they have to take off the thermal shields and redo the whole assembly again. Fix all these welds in the thermal shields. There was concern that there wasn't enough radiation shielding, so the French Nuclear Safety which regulates this, basically shut them down completely, or saying you're not going to start our operation until you address all issues with regard to adequate radiation shielding. So these all these issues are being addressed, and I believe they're going to be addressed adequately. But that means that this machine is not going to, here, let me put it this way. After you get to ITER, so ITER is not going to do DT till 2039. After this, then you have to build a demo reactor. It's not even going to put electricity on the grid, ITER. You have to build another reactor to actually put electricity on the grid. So basically, this ITER path will clearly not lead to fusion, helping avoid 2C or warming and so on.
Right.
So even though, I would just add, even though the Q scientific will be on the order of 10, Q engineering, finally, actually, there's about 400 megawatts. You got 500 megawatts out of fusion power. Actually, finally, you exceed a Q engineering of 1. You obviously need to get much higher, but at least you get in this experiment, if it goes correctly, you would get Q engineering greater than 1. But this is clearly not a fast path to fusion. All right, so I wanted to talk about tritium for a second. I'll try to go through this quickly, actually, because this is a problem in fusion that doesn't get enough discussion into the community. It's kind of why I wanted to hit on it a little bit. There's virtually no natural tritium, as I said, available. Has a half-life of 12.3 years. ITER was going to test out lithium blankets to breed the tritium, but it's not going to use this tritium to go back to use that tritium back into the reactor. All the tritium that it's going to use is going to come from the CANDU reactors, which is these CANDU's Canada deuterium uranium reactors, right? And the reason why they have so much tritium is that these are pressurized heavy water fission reactors, right? So sometimes with heavy water is deuterium, so sometimes the deuterium will absorb a neutron in the fission reaction and turn into tritium, and that's why these CANDU reactors will build up a lot of tritium.
If I may just interject briefly, we're going to hear all about those from Neil Alexander in 2 weeks.
Ah, okay.
So
Okay.
tune in.
All right. All right. So here's the thing too about the CANDU reactors, is that some of them a lot of them were gonna be retired. And so the supply of tritium was going to start decreasing. And then almost all of the tritium in the CANDU reactors was going to go to ITER. So there's almost going to be no tritium left in the world for any other reactor. And this is a huge problem. And this guy, Mohammed Abdu, who did a lot, whose graph I stole from, points out a lot of these issues that, for example, and if you have a 1 gigawatt fusion reactor, it's going to need about 170 kilograms per year of tritium. So it has to make all of its tritium. And the question is, can you actually make enough tritium to run your fusion reactor? This has to be demonstrated. There's no experimental evidence yet that a fusion reactor can make enough tritium to do this. Let's see, a couple of years ago, the National Academy, who I really appreciate actually, did a great in-depth study of fusion, where they came out with this report, bringing fusion to the US grid. Basically what it said is that if we're going to have fusion come in some timely fashion, we need to start building pilot plants in this 2035 to 2040 timeframe. Now, and when you consider this, how difficult this is, because ITER itself, the leading project being constructed right now, isn't even going to get to tritium until 2039. How would you expect that you're going to have pilot plants in this 2035 to 2040 timeframe?
Yeah. And
basically what they said is what they expected basically on this fairly aggressive timeframe, you're going to have a FOAK is first of a kind fusion power plant by 2050. So that was their goal. So obviously, from this respected, there was a lot of heavy hitters in this. So I put a lot of weight into what they were trying to do with this report. But from this report, basically fusion clearly would not contribute to preventing 2C of warming. Okay, so this is basically saying what the where the world's program is going to and what the United States should be doing in terms of investing money in its program.
Joe, the last slide,
Yeah.
was that last statement your statement or theirs?
That's my statement.
That's what I thought.
Yeah,
Okay,
right.
wanted to make that clear. Okay,
Right. They weren't talking about, right. So this is their statements.
sure,
These are in quotes.
sure,
Yeah,
okay,
this is my statement.
sure, good. Just want to be sure.
Right, because my goal was to have fusion address the climate crisis.
Yeah.
And so that's why my talk was framed in this way.
Okay, good. Got it.
My conclusion just simply that this report basically says, okay, we're not going to have fusion in time to prevent 2C warming.
Right.
Okay. They have this. What I liked about this report is that it didn't shy away from all the issues that fusion has to face. I'm going to run through these very quickly. Basically, you need a Q engineering. It basically tells you what you need for your pilot plant. So you're going to make fusion and you're going to have fusion and you're going to put energy on the grid. So obviously Q electric has to be greater than 1. You have to have the electrical power generated by fusion core has to be greater than the electrical power required for operation. It's a pilot plant, so it doesn't have to be incredibly efficient, but it just has to demonstrate this. And the idea for a pilot plant is you can talk about all these things, all the problems that you want to get some data on. Can you recover and process the tritium in a lithium blanket? The materials that face the plasma experience degradation to the plasma because of the plasma. It's going to have thermal loading, ionizing radiation. High energy neutrons are going to degrade this plasma-facing materials. The pilot plant needs to operate for a couple of cycles at least to demonstrate that these components can be repaired and replaced remotely. For availability, it has to demonstrate that you can have at least 50% availability, and you'd want to get up to at least 80% in your first of a kind electrical plant. The alpha particles themselves are going to deposit most of their heat in the plasma, but then what happens is you have these much lower energy alpha particles that are called ash, basically. You need to demonstrate that you can take this ash as well as other impurities and remove them from the plasma. Otherwise, you won't get that plasma burn anymore. So they need to be actively removed from the plasma. This has never been done. All these things basically have never been done before.
That's very important. We got a final question coming in from Alan. Can you handle a quick question from Alan?
Of course.
Go ahead, Alan.
Okay, I just posted that. It's actually 3 questions in one. I'll just put them all out there and then you can just kind of loop them together. One is the cost of these fusion reactors looks to be extraordinarily expensive as opposed to what it takes to build a fission power plant of regular high pressure water. The second part is how are the fission or the fusion reactors to connect to the grid? How is the electricity actually generated?
Yeah, it's just for most of these, it's so let me just take those 2. The first one I'm actually going to answer directly in the next couple of slides.
Okay.
I'll talk about that then. The second one is actually it's just your standard, which is kind of ridiculous in this way, but make steam run a turbine. In some of the advanced fusion cycles, you get charged particles, you could do direct conversion, but nobody's there yet. But it's basically just, boil water, run a turbine. What was your
That's kind of what I imagined.
Yeah. Third
And then
question?
my third question is, do you believe that artificial intelligence is going to help design future reactors?
There was a big article about that by noted plasma physicist Steve Colley in Princeton, who said that. I don't believe it, and I don't believe it. I think it could be helpful, and I've played around a little bit myself with AI, and I don't believe it for the sake that a lot of these are still physics questions, and you don't really get physics intuition from AI per se. You can run a lot of, I think AI is useful because, especially for stellators, it could be incredibly important because, you can have like millions of different stellator configurations, and AI would maybe help zero in on the right configuration. So I believe AI is helpful, but I don't believe at all that it's the answer to fusion. I think improvements in technology and understanding the physics are still the key components to it. But you asked the great question. Actually, your first one is the right question to ask, and I want to answer that actually. I have this one slide, which is almost quaint now, which is that Biden had a plan to develop fusion within the next 10 years. Clearly, with the results last week, this is never going to happen. So I'll just throw out this slide before. I made this slide before last week, so this is totally irrelevant now in terms of what the U.S. is planning to do. But the U.S. was making a lot of strides in both fusion and fission from the federal government, and I think most of that's probably just going to go away.
Yeah.
I'll just won't spend time on that. So here's some of the answer to your first question, which I think is a great question. So the conventional path of fusion, whether it's ITER or laser fusion, clearly isn't going to lead to reactors in times, to meaningfully deal with climate change. So next, what's happening now in fusion is that it's going out of government funding to private fusion companies. And there's an explosion of money in private fusion companies. And I was saying there are 3 fusion companies right in the Madison area right now, right? So this is an enormous recent development. And here you can see funding of fusion as a function of year. And green is the United States. Total right now there's like $9 billion. Even I would be surprised if there was even much more than that, because it's so out of date, these charts. But a lot of the money going to private companies was mostly in the United States, but you could see coming up right behind it is China. China's putting a lot of money into fusion. So there are a lot of startup companies all throughout the United States, and a lot of companies coming in from China, and a few companies coming in from Canada, has a couple, the UK actually, but most of the emphasis is startup companies in the United States, and 3 in the Madison area, and then China has a bunch. So what are these? Oh, so the question I ask is, are private companies going to save the planet? So there's a lot of money coming from venture capitalists. There's a rapid improvement technology that it can easily be accessed. There's a diversity of approaches, which I like, which is, so you look at everything, and they all don't have to succeed. If you had one that was successful, that's great. You would expect most of them to fail. The arguments that I have against it is just that success brings in more money. So companies tend to overpromise, which I dislike. You see that a lot in some of the reports. Many companies don't publish, and which is unforgivable, but they want to keep it trade secret. So it's difficult to gauge what, if any, progress is actually being made from what what could just be a bunch of junk. Here's, I made a slide of, I know that we're getting close to the witching hour, but give me just a few more minutes and I'll be done. But here's a bunch of companies that I just brought up and saying, these people made a bunch of promises. Here's the year of the prediction. That in this year, so in 2009, they predicted that by 2019, they're going to have a prototype fusion reactor. Well, that didn't work. And these are hyperlinks. So I hyperlinked to actually the report where basically they make these statements. People may have, if you pay attention, may have heard this big thing about Lockheed Martin Skunk Works. It was made the news, they were going to have fusion reactors that you could fit on a truck. Well, anyway, this project basically got canceled, shut down in 2021. Tokamak Energy, First Light Energy. Anyway, they all made promises. Helion, I'm going to focus on Helion a little bit more. They made a prediction that they're going to have put electricity on the grid by this year. Well, they only got like a month left or so. So I don't think that they're going to do it. Unfortunately, Zap Energy I actually like. I know the guy who's in the company. I think some of the physics is actually really interesting. Unfortunately, they made this prediction that they were going to get break even last year. It's unfortunate. So this is what happens with private companies. They make these predictions to attract all this venture capital money. So I'm going to pick out. So to answer your question, all these companies are trying to do it faster, cheaper, better. That's essentially the motto. I'm going to pick on two companies. One company that I like and one company that I don't like. So this is a company called Commonwealth Fusion Systems that's worth keeping an eye on. This is a company that was affiliated with MIT. They're making astonishing progress. This is the plant that they already have in Devens, Massachusetts. They have a couple of $1 billion. I thought it was $2 billion, but I wouldn't be surprised if it was more. They have a lot of money now. They made an incredible breakthrough a couple of years ago, which also hit the press, which is that they demonstrated magnetic fields of 20 Tesla using REBCO, which is these rare earth barium copper oxide tapes. These are in form of tapes reinforced by structural metal. And the idea here in essence is you hit the point before. These experiments like ITER are gigantic. You don't want to build a gigantic experiment. So basically, if you up the magnetic field using these what are called high temperature superconductors, you can shrink the size of your plant. So this would be something to watch for. I know some of the people here, they're good physicists. They publish, which is what I give them credit for. They're building a prototype that's supposed to demonstrate break even by, they said at first that was going to be 2025 next year. I know that this machine, that the program has been delayed, so they say it's going to be in 2026. One report that I saw is they're going to achieve break-even by 2027. I wish they hadn't said that, because I think that it's just absurd to build a machine and run it for 1 year and think you're going to get break-even. It takes you that long just to get everything ready and running, see how it operates, and see what some of the problems are. To think that you're going to achieve break-even in 1 year is sort of ridiculous. But these are very credible people. Unfortunately, sometimes make foolish statements. So as I said, it allows for a much more compact device compared to ITER. And they already have this whole magnet fabrication facilities. And these are the people who made like a 17 Tesla coil for Rialta in Stoughton. The company, they have this, these people basically made that coil for the company that's in Stoughton, Wisconsin right now. So I would watch this company. I think they're doing really good work, very credible. They publish their results. Can they do this? It's something interesting. Here's one thing that I'm very skeptical of. There's a company called Helion. And maybe this is what Lou was referring to, I'm not sure, but in 2023, Helion announced an agreement with Microsoft to provide a fusion reactor in 2028. This is backed by Peter Thiel, Sam Altman, and so on, right? They had promised the first ever electricity made by fusion this year already, right? They're behind already in that. And the craziness sort of like of what they expect to do is they're counting on two miracles, which is that first they're not even doing deuterium tritium, they're doing helium-3 to get helium-4 out plus this proton. And so first look, you look, oh great, you don't have to worry about breeding tritium or the fast neutrons activating the walls, except there's no helium-3 on the planet. There's very little. Let me put it this way. Some of it comes from tritium decay. But the second miracle, so first miracle is this. So you have to get as this curve of reactivity is, you have to get even higher temperatures, close to 1 billion degrees Celsius. But not only that, the reactivity comes down. So the prospect of actually getting enough fusion energy out goes down. But the second miracle they're counting on is actually going to breed, because there's no natural source of helium, they're going to breed their helium through these DD reactions. So they're going to have a whole separate plant making helium-3 from breeding DD, which DD is even here, which has an even lower reactivity. And this is going to have some neutrons, and it's going to breed some tritium. So there can be fast neutrons in tritium just to do this thing that you claim is not going to be radioactive, but it is going to be radioactive, and so on and so forth. I think this company here is just a bunch of bullshit, but that's my personal opinion. And we'll see if these guys got they got like at least $1 billion or something from Sam Altman. He's the head of, what is it? Open GPT, I think it is, right? Artificial intelligence guy. Anyway, maybe I'm wrong. Maybe they'll show some great results. So then there are tons of others. I'm not going to go through them all, but I wanted to show you one company that I think is worth looking at, and one company to be skeptical of, and let's just see if they can do anything at all. And this is my final graph. Sorry to take so long, but I wanted to just answer my question. Will fusion help limit the mean surface temperature to below 2C? My answer is no. Electricity from fusion will become a reality. I think fusion will be a reality, but I tend to agree with the National Academy. I think they did a good job sort of understanding what the pitfalls are of fusion, that it really won't have an impact until the second half of the century. And then even if you take the most optimistic assumptions, first of a kind fusion plant comes online in 2035. That's the goal for a lot of these private companies. They all claim they're going to have a pilot plant by 2035. So I was just doing my own calculations, basically saying, what's fusion going to contribute to keeping the temperature down? Basically, so the thing that I use basically is this is a startup of fission power plants, starts like in 1954. You could see it's sort of like this exponential growth. And then you hit like Chernobyl, somewhere around here, and it just flattened out, right? So I just took this part of the curve that, say, fusion follows this path, and I plugged it in to see what you get for fusion in terms of replacing, say, just coal plants. You got a fusion reactor, replace coal plants. What is it I could do to the temperature? And this is the IPCC the temperature expected from that scenario, 4.5. And I plot, this is actually two separate graphs that including fusion, basically starting up in 2035 and taking the path, building as many reactors as fission did in this time period. And you see this curve? It's actually two curves here, but you don't see two curves. And why is that? That's because the impact of fusion even if you follow the fission plant pathway, is so small on the temperature, you can't even see the difference in the curves. So this is my final conclusion. I'll just leave you with this. Even if fusion, basically, let me make this point. Building up fusion reactors following the fission path is too slow. And from my takeaway from this, and my position on energy in general, is it calls for an all hands on deck approach, which is why I particularly don't badmouth any form of energy. It takes everything to get there. Just advocating for more fission plants isn't enough either. I know that's probably not going to sit well with some people here, but that's my opinion, because they won't come online fast enough. And the experience from looking at fission power plants and how long it takes to build, and you can argue with me and tell me the South Koreans are, doing so much better, but it's still not going to do enough. And so basically my attitude is, if you want to bend this curve down and prevent your kids and grandkids from living in a world, which is like 3 degrees hotter, we need to start bending this curve now. And I think what it calls for is an all hands on deck approach, that we do everything. We do fission, we do fusion, we do put solar, we do windmills, we can do everything we possibly can do to bend this curve down. And that's the end of my talk. And if you got a few more minutes, I'm willing to have any other discussion. I know we've gone way over, but I apologize for that. But
we're really way over. But I appreciate very much your comments, Joe, and I salute your voice. It hung in there very well, as well as your ideas.
As somebody who has been long curious about fusion and the state of affairs with it, this is really comprehensive and honest as to the realities of it. I being a evangelist for fission and all electric future, I often have people tell me that it's going to be solar and wind, and then it's going to be fusion, and they just refuse to look at fission. And with this, I've got some ammunition to say that the experts say it's not going to be coming anytime soon.
And sometimes I quote to this group Alex Tanara, who is a very strong proponent of fission only, and I doesn't mean that, even though I appreciate what he has to say, it doesn't mean that's our view. There are many people here in the audience today from a group called Friends of Fission, and every one of us, to the best of my knowledge, advocates for all hands on deck. I don't think anybody has said anything other than that. So I appreciate everything that's been said, and I think it's time to wrap it up.
I know it's time to wrap up. So let me just hit the fission crowd for a second. In this way, that I think what I've tried to do is give a very even-handed approach to where fusion is. I wish other people in other fields, including wind and solar, would do it, and including fission. And one of the things that I don't like, for example, and I've expressed my views on this to many people, is I don't like when fission people dismiss the problems with radiation. There has been, we know from the environmentalists, basically have gotten to the point where they basically make enormous amount of misstatements about what fission does. But on the other side of it, there are people who say that radiation is good for you, that the people working in uranium mines, even though they came out with lung cancer, they got it because they smoked, and not looking at the actual radiation. We saw a bunch of we saw some incidents of hormesis in radioactivity from Mike Connolly's book. I read those papers. The papers are garbage, in my opinion. If you look at them and actually understand what they're doing, there's no credible evidence that hormesis, maybe it's true or not true, but the papers, I've read them, and they're just garbage papers. I wish the fission community I understand that our backs are up against the wall from everybody saying how dangerous fission is. I think that they should have a more realistic point of view. I would like to see other people talk about their energy source in a way that I've tried to project fusion. And that's my.
Thank you for your honesty on fusion again. It's and your comments on fission are well noted.
Right, because let me put it this way. I think it's hurting the fission community. And one of the people who I'll just say right up front, Neil Alexander, if he's going to give a talk 2 weeks ago, he's the guy who gave this talk last spring, and he quoted this report from the Ontario coal miners, and he blamed the uranium miners from getting lung cancer on smoking. And I read that report in depth. And that I wish he could come out and apologize for that statement, because there's no factual evidence whatsoever.
Well, you can ask him in 2 weeks. He'll be here.
He
I
should
think we should wrap it up.
apologize. And this is my problem. This is the danger that the fission community is getting into. When you pick out stuff like that, my tendency is, why do I even want to listen to you?
I don't think you should drop out everything somebody says because you disagree with one particular aspect. I think
That's true.
Neil is a good speaker, and I think you'll have a chance to talk with him in 2 weeks.
But
I'm sorry, we're quarter past the 2 hours, and I think it's time to wrap it up. And thank you, Joe.
sure thing. Take care, everybody.
Bye-bye.
Well, thank you very much.
Thank you, Joe.